Today we're talking about probabilities. First, we'll introduce some very basic definitions. What are probability distributions over discrete and continuous random variables? We'll then talk about how to manipulate probabilities so that they can represent concepts that you care about in your data. And then we'll talk about properties of distributions that allow you to describe distributions and to communicate about what distributions mean. So first, why are we even talking about probabilities? Well, probabilities are the language that we use to describe data. And frankly, data science is about how to get probabilities we care about from data. And in later classes, we'll be using these concepts extensively to build tools and to understand our data. So we really do need these definitions of probability. Because they're so important, you really also need to pay special attention in this lecture and come prepared to work through examples in class. We're also talking about probability now in case you still haven't gotten your R and Rattle setups working. We're only going to be talking about theoretical concepts today. We won't need the laptops, but next week we'll be hitting that really hard. So if you haven't gotten R and Rattle set up on your computing infrastructure, you really should do that now. So first, let's talk about what probability distributions are. Probability allows you to describe random variables. And a random variable is just any probabilistic outcome. For example, the flip of a coin or the height of someone drawn randomly from a population. And sometimes we'll think of quantities that are not strictly probabilities as random variables. So for example, the temperature on a particular day or the number of times street light appears in a document. By definition, random variables have to take on values from some sample space. And this sample space can either be discrete or continuous. For example, a coin flip can only take on a finite number of values, 2. It can either be heads or it can be tails. So the sample space is the set of either heads or tails. In contrast, height can take on all positive real values. Even though it's highly unlikely you'd meet someone who's 500 feet tall, there's no strict upper bound on the height of an individual. Similarly, temperatures can be any real value, and depending on what temperature scale you're using, these temperatures can also be negative. The number of words in a document can take on all positive integers. But there's no upper bound on the number of times you can see a particular word in a document. Each random variable takes on some value in the sample space. We call the realization of any particular random variable an event. We'll denote random variables in the abstract with a capital letter, and realizations of the random variable will be denoted by a lowercase letter. For example, capital X is a coin flip. Little x is one of the values, either heads or tails, of that coin flip. A discrete distribution assigns a probability to every event in the sample space. For example, if your random variable x is an unfair coin, then the probability of getting heads is 0.7 and the probability of tails is 0.3. Every event has a probability assigned to it. By definition, all probabilities must be greater than 0, and probabilities of disjunctions are sums over part of that space. So for example, the probability that a die is bigger than 3 is the sum of the probability of the die being 4, 5, or 6. Also, by definition, the probabilities over the entire space must sum to 1. We'll represent this mathematically by writing this as the sum over all of the outcomes, where sums are symbolized by the capital Greek letter sigma, and just below that sigma we will write the thing that we're summing over. In this case, all of the events in the sample space, little x. And when we sum up over all of the probabilities of realizing that outcome, that has to sum to 1. Now that we've defined probabilities, let's talk about how you can work with them. So an event is a set of outcomes to which a probability has been assigned. One event might be drawing a black card from a deck of cards, or drawing a king of hearts. Given particular events, you can talk about intersections and unions of those events. So for example, the intersection of two events, where one event is drawing a red card and another event is drawing a king, is the intersection of those two events. So what is the probability of drawing a red king? We can think about this geometrically. If we think about events A and B as having some probabilities, where the total area of the shapes A and B represent the probabilities of those events, the probability of their intersection is just the area where these events overlap. So when is it the case that both A and B happen? For the example of a deck of cards, it's when your card is both a red card and a king. For a union, we need to be a little bit more careful. When you combine two events A and B, you want either event to be true. Both of them don't have to be true. So if you have the probability of two individual events A and B, you need to subtract out their intersection so you don't double count it. So if you want the probability of drawing a card that is either a spade or a king, you have to add the probability of getting a spade plus the probability of getting a king, and then subtract out the probability of the intersection getting the king of spades. If you don't do that, you're overcounting. Often, probabilities over multiple random variables are expressed as a joint distribution. And you can think about this as having some collection of outcomes in your sample space, and every configuration of random variables is assigned a probability. For example, if you have 4 coins, there are 16 possible outcomes. Each of them has some probability. And again, we can represent this geometrically. Whereas if you have a single random variable that's binary, your event space is partitioned between x being true or false. But if you add in an additional binary random variable, you now have to distinguish among 4 cases. X and y can both be false, x and y can both be true, and there are 2 ways that either x or y can be true and the other false. So what happens if you're given a joint distribution, but you actually want a distribution in terms of a single random variable? When you get this, you have to use a technique called marginalization. What marginalization does is it takes a joint distribution and then sums over all of the possible outcomes for the random variables that you don't care about so that you can get the distribution that you do care about. For example, if you have a joint distribution of x, y, and z, and you only care about x, you have to sum over all of the possible outcomes of the random variables y and z to recover your distribution over the random variable x. This is clear with an example. So let's say that you have a joint distribution over 2 random variables, one for the temperature and one for the weather. First, let's assume that you only care about the weather. When you marginalize out the random variable corresponding to temperature, this produces a new table with a smaller number of cells than the original table that represented the joint distribution. So first, let's say that you want to compute the marginal probability of the temperature being hot. So you need to look at your original joint distribution. What are all of the configurations of random variables where the temperature was hot? In this case, there are 2 of them. So marginalization tells you have to sum these 2 together to get the marginal probability of the temperature being hot. When you add those 2 together, you get 0.15. You can do the similar calculation for the temperature being mild or cold. If we want to marginalize out temperature, we now have a table with two entries, one for the weather being sunny or the weather being cloudy. So if we want the probability of the weather being sunny, we look at the original joint distribution and all of the configurations where the temperature took on any value but where the weather was sunny. There are three outcomes like this, and we add them all together and we get the probability of 0.4. We can do the same thing for cloudy. Another common probability that we'll work with is the notion of conditional probabilities. The conditional probability is defined as the probability of event A given that you already know B occurs. In terms of notation, we'll write this as the probability of A given B, where the vertical bar between A and B is read as given by. So the probability of A given B. Mathematically, this can be derived by taking the probability of the intersection of A and B dividing by the probability of B. We can also think about this geometrically. If you have your original outcomes, A and B, by conditioning, you're essentially throwing out all of the outcomes where B does not occur. So now you restrict yourself to this outcome space, and you want to know, of these outcomes, what is the proportion of events where A happens? Let's see an example. Let's say that you want to compute the probability that the sum of two dice is 6, given that the first die is greater than 3. We'll represent this using two random variables, A and B. And I've highlighted all of the outcomes where A is greater than 3. You'll notice that in this joint probability distribution, there are 36 outcomes, and because these are fair dice, each outcome has probability 1/36. In red, I'll mark all of the outcomes where the sum of the two dice is 6. Given our formula for conditional probability, we now need to compute two probabilities, the probability of the intersection of these two events and the probability of the thing that we are conditioning on. In this case, the probability that the first die is greater than 3. So let's go through each of these. So the probability of A being greater than 3 and the sum of the two dice being 6 is simple. There are only two ways to get the sum of the two dice being 6 when A is greater than 3. If A is 5, B has to be 1. If A is 4, then B has to be 2. So 2 out of 36 of our outcomes satisfy the condition that A is greater than 3 and the sum of the two dice is 6. Now how about the probability of A being greater than 3? Well, there are 16 over 36 outcomes where that's true, or if you just think about a single die, half of the outcomes have A greater than 3. So we can plug these values into the formula for conditional probability. We have 2 over 36 divided by 3 over 6. And when we simplify this fraction, this gives us 1/9. You could have also calculated this by just looking at the yellow area and thinking about it geometrically. There are a total of 18 outcomes in the yellow area, the thing that we're conditioning on, and 2 of them have the sum of the two dice being 6. So 2 over 18 equals 1/9. It isn't always so straightforward, though. Often you'll need to appeal to the regular formula for computing conditional probabilities. often what you need to do is to turn one kind of probability distribution into another. Now we're going to go through some examples of that. First, let's say that you have a conditional distribution and you want to get out of that a joint distribution. To derive a formula for how you can get a joint distribution, such as the probability of x and y, from a conditional distribution, first take a look at the probability of x and y. We can multiply this by 1, or the probability of y over the probability of y. We can take the probability of x and y over the probability of y and replace that by the conditional probability of x given y. This is just the definition of conditional probability. So now we have a formula relating conditional probabilities to joint probabilities. And notice that the only additional piece you need is the marginal probability of y, which you could compute using marginalization. For example, let's say that you have information about conditional probabilities given symptoms. Given these conditional probabilities and the probability of the overall prevalence of the symptom in the population, you can compute the joint probability of the symptom and the disease. In general, for any set of n variables, you can create a joint distribution by conditioning each variable on all the others. Another common problem is when you have a conditional probability distribution, but it's going in the wrong way. You want the probability of b given a when you only have the probability of a given b. These are related to each other using a very famous formula called Bayes' rule that allows you to flip the direction of the conditionality. You first start with the probability of a given b, then you change the outcome space from b, the events where b happens, to the entire sample space. And then you change it again by dividing by probability of a. So you go from b to the entire space, then back to a, so that you have the right conditional distribution. We can also see this graphically. You first start with a conditional probability distribution where you're only looking at events where b occurs. You then expand that out to the entire event space, and then restrict it back down to a different conditional space. One property that comes in very handy when we're working with these probability distributions is the notion of independence. X and y are said to be independent if their joint probability is equal to the product of their marginal probabilities. One very useful property of independence is that if x and y are independent, then conditioning on y gives you no additional information about x. So mathematically, if you have two socks that you draw from the laundry, is the color of the first sock independent from the color of the second sock? No. One obvious example of this is, let's say that you have 19 white socks and one black sock. If you know the color of the first sock that you pull out of the laundry is black, you know much more about the possible colors of the second sock. However, if you think about coin flips, knowing the outcome of the first coin flip tells you nothing about the outcome of the second coin flip, so long as you have a fair coin. Because independence is so important, let's spend a little bit more time on examples of independence. So here are some examples of things that one could reasonably say are independent. That you use a Mac and that the green line is on schedule. That the amount of snowfall in the Himalayas is independent of your favorite color being blue. Now, of course, if you have a hyperactive imagination, you could imagine a story connecting these two things, but it's fairly reasonable to assume that these are independent. We can also think about events that are definitely not independent. So you voting for Mitt Romney is not independent of you being a Republican. There being a traffic jam on the Beltway is not independent of whether or not the Redskins are playing. So while these are very clear examples, sometimes this distinction isn't so clear-cut. Sometimes we make very convenient assumptions. Whether it is raining in the number of taxi cabs is probably not independent, but we may assume that it is. Similarly, the first two words in a sentence are definitely not independent. If the first word in a sentence is an, A-N, then you know that the second word in the sentence is likely to start with a vowel. But often in applications, we will make independence assumptions even if they're not strictly true. Thus far, we've mostly been talking about discrete distributions, the color of a sock, the outcome of a roll of a die. However, we're not going to restrict ourselves to discrete distributions in this class, so we now need to talk a little bit about how the concepts that we've talked about thus far also apply to continuous distributions. Whereas before, we said that discrete distributions have to sum to 1, the analog for a continuous distribution is that the probability distribution has to integrate to 1. Instead of asking what is the probability of a single outcome, you now have to talk about the probability of certain intervals. What is the probability of an outcome being between -2.4 and 6.5, for instance? Here, the distinction between lowercase and uppercase letters becomes more important. This is because the lowercase letters represent densities, and the uppercase letters represent events. Now at this point, you may be saying, whoa, integrals, I didn't sign up for this. Like I said before, we won't be asking you to compute any integrals, but you do need to be able to think about these things intuitively. So let's look at an example. You may have heard about the normal distribution before. If you take the entire normal distribution and compute the entire area under this curve, that has to sum to 1 because it is a probability distribution. This is equivalent to us saying that a discrete distribution has to sum to 1. Similarly, we can cut the normal distribution in half. Everything to the right of our cut has probability 0.5. Everything to the left of our cut has 0.5. This is because the normal distribution is symmetric. And integrals, if you've taken calculus, is just a fancy name for taking the area under a curve. Between 0 and 1, there is a 34% chance that you will land under that part of the curve. Between -1 and 1, there is a 68% chance that you'll land in that part of the curve. This is all we're talking about when we talk about probability densities. And the ranges are simply integrals that you can look up in a table. So this is what the normal distribution looks like graphically, but we can also write it mathematically. And the mathematical definition of the normal distribution looks like this. It's defined by two parameters, mu, and mu represents the mean, and sigma squared is called the variance. Now that you've seen the mathematical form, let's go back to the picture so it will make more sense. So a normal distribution can be defined by these two parameters. The mean represents where on the x-axis the bump is. If the mean is 0, then the normal distribution will be centered around 0. So the mean shifts the peak of the normal distribution left or right. The variance sigma controls how peaky or how pointy the distribution is. When sigma becomes very small, it looks like a very sharp peak. When sigma is very wide, it looks like a soft rolling hill. That's all I wanted to say about continuous distributions right now. You'll hear more about it when we talk about regressions, but this should tide you over until then. The last thing that we're going to talk about today are two mathematical descriptions of probability distributions that we can use to understand the properties of a distribution. They are expectation and entropy. We represent expectations by a capital letter E. The expectation of a function f is represented by E square brackets around the function f. Then we evaluate that function f over the support of the distribution, multiplying the function f by the probability at each point x. For discrete distributions, this amounts to a sum. For continuous distribution, this amounts to an integral. If the function that you're computing the expectation of is a constant, then the expectation of that constant is that constant, obviously. Similarly, if you condition on a random variable taking on a specific value, and then compute the expectation of that random variable, you will get the value that you conditioned on. This is because you have taken all of the uncertainty out of the distribution and placed it only on a single point. This is all very abstract, so let's take a look at an example. If we compute the expectation of a Gaussian distribution, then this is x times the probability density of a Gaussian distribution, integrated over the entire space. Even though this is a very nasty integral, we know from the shape of a normal distribution that it's centered around its mean. So if you take the expectation of this, you will simply get the mean of the distribution back out. That's because the normal distribution is symmetric. More intuitively, we can think about the expected value of a distribution as the center of mass of this distribution. If you had your distribution on a teeter-totter, where the probability mass weighed down on this teeter-totter, the point on the distribution where everything is perfectly balanced is the expected value of the distribution. If you also think about the probability distribution as a payoff, in terms of gambling, say, the fair price of a wager is the expected value. Now let's take a look at another example on discrete distributions. So what's the expectation of a roll of one die? So this requires us to go through and take the outcome of each die and then weight it by its probability. The probability of each outcome is just 1/6 because it's a fair die. So if you add up the numbers 1 through 6, you get 21. 21 divided by 6 is 3.5. That was fairly easy, so let's look at a more complicated example. What is the expectation of the sum of two dice? So now the probabilities are no longer all the same. Some outcomes are more probable than others. However, what we can do is we can use the linearity of expectations, and if the expectation of one die is 3.5, then the expectation of two die will be twice that because the two die are independent. And if you work out the math, you get 7 even if you calculate this complicated formula. In general, all you have to do is take the outcome and multiply it by its probability. This gives you the expected value. While the expectation in and of itself is very important, It's also a key building block of the other property that we're going to be talking about, entropy. Entropy is a term that comes from physics. And in physics, entropy is the measure of the disorder in a system. One fundamental law of physics is that the entropy in a system tends to increase over time. But this concept can also be applied to probability. If all of your outcomes are equiprobable, then there is a lot of disorder in the system and you have high entropy. And as we'll see in future lectures, we often want to use entropy to encode how uncertain we are about the inferences we're making from data. So entropy is our friend. When we don't know the answer, all else being equal, we want to seek models and distributions that have maximum entropy. Before we can talk about entropy, I want to very briefly review the concept of logarithms. At a very high level, logarithms are a function that make big numbers small. And one way to think about them is in cutting a carrot. So let's say that you want to cut a carrot into X pieces. The logarithm tells you how many separate cuts you would need in order to get that number of pieces. So if you only want to have one piece, you need to make 0 cuts. The carrot is already in one piece, so that's fine. If you want to have 2 pieces of carrot, you need to make 1 cut to cut it into 2. If you want to cut your carrot into 4 pieces, you need to make 2 cuts. Once to cut the original carrot into half, and then you can put the 2 halves of the carrot together and then cut that again. Similarly, if you want to cut the carrot into 8 pieces, you need to make 3 cuts. Once to cut it into halves, another cut to cut it into quarters, and then one final cut to cut your quarters into an eighth. Logarithms, however, are not just defined for integers, they're also defined for decimal numbers and for numbers between 0 and 1. However, you cannot get negative pieces of a carrot, and so you cannot take the log of a negative number. Those preliminaries aside, we can now define the entropy function. The entropy function is just the negative expectation of the log of the probability distribution. When we plug that into the definition of entropy, this means that we sum or integrate over every outcome in our event space, and we multiply the probability of the outcome times the log of the probability of the outcome. So notice that this does not account for the values of the random variable at all, only the spread of the distribution. What does the distribution look like? Notice that x is never involved, it's only p of x. So one property is that if you have a uniform distribution where every outcome is equally likely, that gives you the maximum entropy. To double check that the entropy doesn't care about the values of the distribution, consider 2 discrete distributions that have 2 outcomes. One has outcome 0 and 1, and the other one has outcome 0 and 100. So long as they weight their 2 outcomes equally, they have the same entropy. In class, we'll work through some examples for both 1 die and 2 dice. I realize this has been a lot of material, so that's it for now. We'll review this stuff in class and answer your questions. I'm sure you'll have a lot of them, but hopefully this has gotten your feet wet and you'll be ready to really absorb these concepts when we go over examples in class. Today we focused on the mathematical foundations, but next week we're going to be focusing on the technological foundations, dealing with messing data and telling stories with data. So if you haven't gotten your environment set up for R and Rattle, then if at all possible, try to do so before the following week. See you on Monday.